In mathematics, a Pisot Vijayaraghavan number, also called simply a Pisot number or a PV number, is a real algebraic integer greater than 1 such that all its Galois conjugates are less than 1 in absolute value. These numbers were discovered by Axel Thue in 1912 and rediscovered by G. H. Hardy in 1919 within the context of Diophantine approximation. They became widely known after the publication of Charles Pisot's dissertation in 1938. They also occur in the uniqueness problem for Fourier series. Tirukanapuram Vijayaraghavan and Raphael Salem continued their study in the 1940s. Salem numbers are a closely related set of numbers. A characteristic property of PV numbers is that their powers approach integers at an exponential rate. Pisot proved a remarkable converse. If alpha greater than 1 is a real number such that the sequence measuring the distance from its consecutive powers to the nearest integer is square summable, or 2, then alpha is a Pisot number. Building on this characterization of PV numbers, Salem showed that the set S of all PV numbers is closed. Its minimal element is a cubic irrationality known as the plastic number. Much is known about the accumulation points of S. The smallest of them is the golden ratio. Definition and properties. An algebraic integer of degree n is a root alpha of an irreducible monic polynomial p of degree n with integer coefficients, its minimal polynomial. The other roots of p are called the conjugates of alpha. If alpha greater than 1 but all other roots of p are real or complex numbers of absolute value less than 1, so that they lie strictly inside the circle x equals 1 in the complex plane, then alpha is called a Pisot number, Pisot Vijayaraghavan number, or simply PV number. For example, the golden ratio, phi 1.618, is a real quadratic integer that is greater than 1, while the absolute value of its conjugate, minus phi minus 1 minus 0.618, is less than 1. Therefore, phi is a Pisot number. Its minimal polynomial is x2 minus x minus 1. Elementary properties. Every integer greater than 1 is a PV number. Conversely, every rational PV number is an integer greater than 1. If alpha is an irrational PV number whose minimal polynomial ends in k, then alpha is greater than k. Consequently, all PV numbers that are less than 2 are algebraic units. If alpha is a PV number, then so are its powers alpha k, for all natural number exponents k. Every real algebraic number field k of degree n contains a PV number of degree n. This number is a field generator. The set of all PV numbers of degree n in k is closed under multiplication. Given an upper bound m and degree n, there are only a finite number of PV numbers of degree n that are less than m. Every PV number is a parent number. Diophantine properties. The main interest in PV numbers is due to the fact that their powers have a very biased distribution. If alpha is a PV number and lambda is any algebraic integer in the field, then the sequence where x denotes the distance from the real number x to the nearest integer approaches 0 at an exponential rate. In particular, it is a square summable sequence and its terms converge to 0. Two converse statements are known. They characterize PV numbers among all real numbers and among the algebraic numbers. Let alpha be a real number greater than 1 and there exists a non-zero real number lambda such that then alpha is a Pisot number and lambda is an algebraic number in the field. Let alpha be an algebraic number greater than 1 and there exists a non-zero real number lambda such that then alpha is a Pisot number and lambda is an algebraic number in the field. A long-standing Pisot Vijayaraghavan problem asks whether the assumption that alpha is algebraic can be dropped from the last statement. If the answer is affirmative, Pisot's numbers would be characterized among all real numbers by the simple convergence of lambda alpha n to 0 for some auxiliary real lambda. It is known that there are only countably many numbers alpha with this property. The problem is to decide whether any of them is transcendental. Topological properties. The set of all Pisot numbers is denoted S. Since Pisot numbers are algebraic, the set S is countable. Raphael Salem proved that this set is closed. It contains all its limit points. His proof uses a constructive version of the main Diophantine property of Pisot numbers. Given a Pisot number alpha, a real number lambda can be chosen so that 0 less than lambda alpha and thus the 2 norm of the sequence, lambda alpha n, can be bounded by a uniform constant independent of alpha. In the last step of the proof, Pisot's characterization is invoked to conclude that the limit of a sequence of Pisot numbers is itself a Pisot number. Closedness of S implies that it has a minimal element. Carl Ludwig Siegel proved that it is the positive root of the equation x3 minus x minus 1 equals 0 and is isolated in S. He constructed two sequences of Pisot numbers converging to the golden ratio phi from below and asked whether phi is the smallest limit point of S. This was later proved by de Fresnoy and Pisot, who also determined all elements of S that less than phi. Not all of them belong to Siegel's two sequences. Vijayaraghavan proved that S has infinitely many limit points. In fact, the sequence of derived sets does not terminate. On the other hand, the intersection of these sets is empty, meaning that the Cantor-Bendixson rank of S is omega. Even more accurately, the order type of S has been determined. The set of Salem numbers, denoted by T, is intimately related with S. It has been proved that S is contained in the set T of the limit points of T. It has been conjectured that the union of S and T is closed. Quadratic irrationals. If is a quadratic irrational, there is only one other conjugate, obtained by changing the sign of the square root in from or from. Here A and D are integers, and in the second case A is odd and D is congruent to 1, modulo 4. The required conditions are alpha greater than 1 and minus 1 less than alpha less than 1. These are satisfied in the first case exactly when A greater than 0 and either or. These are satisfied in the second case exactly when and either or. Thus, the first few quadratic irrationals that are PV numbers are powers of PV numbers. Pisot Vijayaraghavan numbers can be used to generate almost integers. The nth power of a Pisot number approaches integers as n approaches infinity. For example, since n differ by only as extremely close to indeed higher powers give correspondingly better rational approximations. This property stems from the fact that for each n, the sum of nth powers of an algebraic integer x and its conjugates is exactly an integer. This follows from an application of Newton's identities. When x is a Pisot number, the nth powers of the other conjugates tend to 0 as n tends to infinity. Since the sum is an integer, the distance from xn to the nearest integer tends to 0 at an exponential rate. Small Pisot numbers. All Pisot numbers that do not exceed the golden ratio phi have been determined by de Fresnoy and Pisot. The table below lists 10 smallest Pisot numbers in the increasing order. The polynomials in this table, with the exception of a factors of either or, the first polynomial is divisible by x2 minus 1 when n is odd and by x minus 1 when n is even. It has one other real zero, which is a PV number. Dividing either polynomial by xn gives expressions that approach x2 minus x minus 1 as n grows very large and have zeros that converge to phi. A complementary pair of polynomials, and yields Pisot numbers that approach phi from above. Since these PV numbers are less than 2, they are all units. Their minimal polynomials end in 1 or minus 1.